Q7324. The lighter workloads associated with glass, digital, flight instrumentation. A. Are instrumental in decreasing flight crew fatigue. B. Have proven to increase safety in operations. C. May lead to complacency by the flight crew. The correct answer is C. Glass flight instrumentation refers to the use of digital displays and advanced technology in aircraft cockpit instrumentation. These systems offer numerous benefits, including improved situational awareness, enhanced data presentation, and simplified information management. However, the lighter workloads associated with glass flight instrumentation can potentially lead to complacency among the flight crew. Here's why. 1. Reduced physical and mental workload. Glass flight instrumentation streamlines information presentation and reduces the physical and mental workload traditionally associated with analog instrumentation. The automation and integration of data provide pilots with easier access to essential flight parameters and navigation information. While this can enhance efficiency and reduce pilot workload, it also creates the risk of complacency. 2. Decreased vigilance. With reduced workload, pilots may become less vigilant and attentive to critical flight tasks. The automation and digital presentation of information can create a sense of reliability and reduce the perceived need for constant monitoring. Pilots may start to rely heavily on the automation without maintaining a proactive approach to flight management and situational awareness. 3. Over-reliance on automation. The advanced capabilities of glass flight instrumentation may lead to an over-reliance on automation. Pilots may trust the automation systems to perform flawlessly and handle all aspects of the flight. This over-reliance can erode manual flying skills, reduce the ability to detect automation errors or malfunctions, and hamper the readiness to take over manual control in case of automation failure. 4. Decreased attention to cross-checking. The lighter workload associated with glass flight instrumentation can lead to reduced attention to cross-checking and verifying information. Pilots may be more inclined to accept the presented information without independently verifying it against other sources or conducting thorough cross-checks. This can increase the risk of accepting erroneous or misleading data. 5. Inadequate response to abnormal situations. Complacency resulting from lighter workloads can impair the ability of the flight crew to respond effectively to abnormal or emergency situations. The lack of continuous engagement and monitoring can delay the recognition of critical events and hinder timely decision-making and appropriate actions. To mitigate the potential risks associated with complacency, pilots must maintain a proactive approach to flight operations, continuously monitor the automation systems, and remain proficient in manual flying skills. Ongoing training, standard operating procedures, and effective crew resource management are crucial in maintaining situational awareness and ensuring a high level of safety in operations. 6705. An electrical system failure, battery, and alternator, occurs during flight. In this situation, you would A. Experience avionics equipment failure. B. Probably experience failure of the engine ignition system, fuel gauges, aircraft lighting system, and avionics equipment. C. Probably experience engine failure due to the loss of the engine-driven fuel pump, and also experience failure of the radio equipment, lights, and all instruments that require alternating current. The correct answer is A. Avionics equipment dependency on electrical power. Avionics equipment refers to the electronic systems and instruments used for navigation, communication, and monitoring in an aircraft. These systems rely on electrical power to function properly. They are typically powered by the aircraft's electrical system, which includes the battery and alternator. Impact of electrical system failure. When the electrical system fails due to the loss of both the battery and alternator, there is no power source available to supply electrical energy to the avionics equipment. As a result, the avionics equipment will experience a failure and become inoperative. This can include instruments such as the radio, navigation systems, transponder, flight displays, and other electronic devices used for communication and navigation. Loss of critical information and functionality. Avionics equipment plays a crucial role in flight operations, providing important information to the pilot and supporting safe and efficient flight. When the electrical system fails, the loss of avionics equipment can result in the inability to communicate with air traffic control, navigate accurately, monitor critical flight parameters, and access important flight data. This can significantly impact situational awareness and the ability to safely operate the aircraft. Limited functionality without electrical power. Some aircraft systems and instruments may have backup power sources or battery backup capabilities to provide limited functionality in the event of an electrical system failure. However, these backup systems are typically designed to provide basic functionality for a limited duration. They may not support the full operation of avionics equipment, and their capacity may vary depending on the aircraft's design and configuration. It's important to note that the specific impact of an electrical system failure can vary depending on the aircraft's design, electrical system configuration, and the availability of backup power sources. The aircraft's manufacturer documentation and emergency procedures should be consulted for guidance on handling an electrical system failure and the associated implications for avionics equipment. 6707. What precautions should take with to aircraft oxygen systems? A. Ensure that only medical has to replenish oxygen containers. B. Prohibit smoking while in an aircraft with a portable oxygen system. C. Ensure that industrial oxygen has not been used to replenish the system. The correct answer is C. Oxygen system requirements. Aircraft oxygen systems are designed to provide supplemental oxygen to the crew and passengers when flying at high altitudes where the oxygen concentration in the atmosphere is insufficient for normal respiration. The oxygen is stored in cylinders or containers and delivered through a regulated system to the individuals who require it. Purity and compatibility of oxygen supply. It is essential to ensure that the oxygen used to replenish the aircraft's oxygen system is of the appropriate quality and purity. Industrial oxygen, which is used for industrial processes, may not meet the necessary standards for aviation oxygen. Industrial oxygen can contain impurities or contaminants that may be harmful or incompatible with the aircraft's oxygen system. Therefore, using industrial oxygen to replenish the aircraft's oxygen system can pose safety risks and compromise the system's functionality. Proper oxygen source. To maintain the integrity and safety of the aircraft's oxygen system, it is important to use only approved and properly regulated oxygen sources. This typically involves using medical-grade oxygen, which meets the required purity standards for aviation use. Medical-grade oxygen is specifically produced and handled to ensure its safety and compatibility with the aircraft's oxygen system. Compliance with regulations. Aviation authorities and regulations specify the requirements for oxygen systems and their maintenance. These regulations often include guidelines and standards for the sourcing, handling, and replenishment of oxygen in aircraft. Following these regulations is crucial to ensure the safe operation of the aircraft and the well-being of the occupants. By ensuring that industrial oxygen has not been used to replenish the aircraft's oxygen system, the risk of using incompatible or impure oxygen is minimized. This helps maintain the proper functioning of the oxygen system and ensures the safety of the crew and passengers on board. It's important to note that in addition to the precautions mentioned there may be other precautions and procedures specific to the aircraft and oxygen system in use. Pilots and operators should consult the aircraft manufacturer's documentation, maintenance manuals, and applicable regulations for comprehensive guidelines on the proper handling and maintenance of aircraft oxygen systems. 6708. What type of oxygen system is most commonly found in general aviation aircraft? A. Demand. B. Continuous flow. C. Pressure demand. The correct answer is B. Continuous flow oxygen system. A continuous flow oxygen system is a type of oxygen system that provides a constant flow of oxygen to the user, regardless of their breathing pattern or demand. The oxygen is delivered at a fixed rate, typically measured in liters per minute, (LPM). The continuous flow system ensures a steady supply of oxygen to the user, allowing them to breathe comfortably and maintain adequate oxygenation. General aviation aircraft. General aviation refers to non-commercial, private, and recreational aviation activities. This category includes a wide range of aircraft, such as small propeller-driven airplanes, light jets, and helicopters. General aviation aircraft are commonly used for personal transportation, flight training, and recreational flying. Oxygen requirements in general aviation. While general aviation aircraft typically operate at lower altitudes compared to commercial airliners and military aircraft, there are scenarios where supplemental oxygen is necessary. These include flying at higher altitudes where the oxygen concentration in the atmosphere is insufficient for normal respiration, or during aerobatic maneuvers where high G-forces can cause hypoxia. Suitability of continuous flow systems. Continuous flow oxygen systems are commonly used in general aviation aircraft due to their simplicity, reliability, and ease of use. These systems provide a steady flow of oxygen to the user, ensuring a constant supply even during varying breathing patterns or demands. They are generally well suited for general aviation operations where a constant and reliable oxygen supply is sufficient. While other oxygen system types, such as demand or pressure demand systems, are also used in aviation, continuous flow systems are more commonly found in general aviation aircraft. Demand systems deliver oxygen only when the user initiates a breath, while pressure demand systems deliver oxygen based on the user's breathing rate and the cabin altitude. These types of systems are more commonly used in high-performance aircraft or specialized operations. It's important to note that the specific type of oxygen system installed in a general aviation aircraft can vary depending on the aircraft model, owner preferences, and regulatory requirements. However, in general, continuous flow systems are widely used in general aviation due to their simplicity and effectiveness. 6709. What of oxygen should to replenish an aircraft oxygen system? A. Medical. B. Aviation. C. Industrial. The correct answer is B. Aviation oxygen. Aviation oxygen refers to oxygen specifically manufactured and approved for use in aircraft oxygen systems. It is designed to meet the specific requirements and standards set by aviation authorities and regulatory bodies. Aviation oxygen is commonly available in compressed gas or liquid form and is stored in specialized cylinders or reservoirs within the aircraft. Replenishing the aircraft oxygen system. Replenishing the aircraft oxygen system involves refilling or replacing the oxygen supply to ensure an adequate and continuous oxygen source for the occupants. This is typically done by connecting the oxygen source, such as a refillable cylinder or a portable oxygen system, to the aircraft's oxygen system. Importance of using aviation oxygen. It is crucial to use aviation oxygen to replenish the aircraft oxygen system for several reasons. A. Purity and safety. Aviation oxygen is manufactured and processed to meet strict quality standards, ensuring high purity levels and eliminating contaminants that may be present in other oxygen sources. Using aviation-grade oxygen helps maintain the safety and effectiveness of the oxygen system. B. Compatibility. Aviation oxygen is specifically formulated to be compatible with the materials and components used in aircraft oxygen systems. Using other types of oxygen, such as medical or industrial oxygen, may introduce compatibility issues that can compromise the integrity and functionality of the oxygen system. C. Regulatory compliance. Aviation authorities, such as the Federal Aviation Administration, FAA, in the United States, mandate the use of aviation oxygen in aircraft oxygen systems. Compliance with these regulations is essential for safe and legal operation of the aircraft. Other types of oxygen. While medical and industrial oxygen may be suitable for their respective applications, they are not intended for use in aircraft oxygen systems. Medical oxygen is specifically formulated for medical purposes and may not meet the stringent requirements and specifications of aviation oxygen. Industrial oxygen is intended for industrial processes and may contain impurities or be of a different purity level than aviation oxygen.